Everything okay? Yeah, no worries. It was quick, right? So it's like on a Formula One contest, you change the tires quickly and then go to the next lap. No worries. Okay, we are in a family, a network science family, so I hope. So it is my pleasure to introduce not one, but two speakers. So Naomi Arnold and Ben Steer. I hope I pronounced it correctly. Although I should say, before even talking a bit about yourself, that I'm not completely sure on how to pronounce Raphtory.
That's it, yeah.
The authors can say, so how should I say it?
Raphtory is a...
Raphtory. So you're I think it was done also during our PhD, so your way is the correct way. Right? So should I say MySQL, MySQL? Let's not vote that, or I think
it's a temporary name that's stuck, I think is the problem. Nothing is more permanent than a temporary name.
Yeah. So both Naomi and Ben come from the Queen Mary University of London, although Ben has also steered two more private companies. So I think you are the Chief Technical Officer and founder of Temporal. So not a sponsorship, but still. So it is my pleasure to welcome you, and they will talk about Raphtory, which is an open source distributed real-time temporal graph analytics platform. So hopefully, for instance, when you want to analyze the cooperation and simulate it quickly, for instance, we can use distributed platforms such as yourself. So without further ado, Naomi, the floor is yours.
Thanks, Pedro, and thanks for having us. It's been a really nice day so far, and it's nice to be here in person as well. Doing a great set of talks. Yeah, as Pedro said, I'm Naomi. I'm a postdoc at Queen Mary, University of London. I'm here with Ben and Felix as well, who I'll introduce in the next couple of slides, and be talking to you about our system, Raphtory. So Raphtory, in a nutshell, is a platform for analysing temporal networks or graphs. And in this platform, you can read in or ingest graph data from anywhere, different sources. You can run a variety of inbuilt algorithms that we've written, or write your own using the API. And it's something that can be deployed on something as small as your laptop or local machine, or be scaled up across a cluster or in the cloud like AWS somewhere as well. And Raphtory has been around for, I guess, a few years now, and has a nice and growing community around it. So it started when Ben Steer created it as part of his, well, as his PhD, being supervised by Felix, and this was at Queen Mary. And then in the later years of my PhD, I've been using Raphtory on a couple of my data sets that we're working on as a project, which I'll talk about a little bit later. I'm working on the open source Raphtory as part of my postdoc now. Felix is now a professor at UPM and has some students working on Raphtory and developing that and using on their data sets. And then most recently, Ben and some colleagues founded the startup called Pometry, which is developing partly the open source, but an enterprise version of Raphtory, which is being used in both sort of research and more industry use cases. And there are many more wonderful people involved in the Raphtory project, but as you can see, the graph was getting slightly cluttered to try and include them all in. So in this tutorial session, and hopefully we're going to show you how Raphtory works, and by the end of it, if you find that it's something that's helpful for your use case or a data set that you're looking at, that would be a fantastic outcome. We're going to show you around the Raphtory API and how to actually interact with the software, from writing algorithms to reading in and making queries on your data. And we're going to end with a demo. We're using an example from The Lord of the Rings and their interaction and the character interactions throughout. Just before that, though, we'll take a quick look at what Raphtory has been used for, some examples. And it's been used a little bit across both academic research side and some industry use cases as well. So in this, just last year, we published a paper with Queen Mary and UPM looking at an interesting data set of interactions from an alt-right social media platform called Gab. And we'll look at this example in a little bit more detail later on, but we're interested in how the structure of their interactions were changing over time as a graph. Some researchers at Mishcon-Dereya, a legal firm in UCL, were using Raphtory to study a 400-year-long data set of legal citations when one case cites another to study how the influence changes over time. It's been used at the moment to look at temporal motifs in some other things in crypto networks of transactions, seeing if you can identify different services or potential bad actors by the temporal motifs that they're showing in their interactions. And then another industry use case is looking at the spatial and temporal co-location of boats. So, for example, if two large vessels meet somewhere in the middle of the ocean when they shouldn't be, perhaps there's something that can be studied as a graph that's evolving in time. So to give a bit of background of both Raphtory and, to some extent, temporal graphs, when we talk about graphs in networks, classically we think of networks as a sort of static, unchanging snapshot, and a lot of the original metrics and ways of reasoning graphs were looking at it from quite an unchanging in time perspective. But as we probably all know, many systems that we model as graphs do change in time, and drawing quite early on into the Lord of the Rings example, if we're thinking about their interactions as a graph, at the start of the books and the film, Gandalf is mainly interacting with the hobbits over in the Shire, and as the plot evolves, moves over to be interacting more primarily with people like Legolas and Aragorn, and this constitutes quite a big change in the plot arc. And we wouldn't necessarily see that if we were just looking at the static graph of interactions. But what I talked about, the potential viewing as a temporal graph, the first way that we might think of modeling it is just different snapshots of the graph over time. So the two interactions that start on this one, moving into a triangle of interactions later on. And sometimes that is enough, the viewing sort of fairly coarse snapshots. But depending on the data set and use case, sometimes you have like much more fine-grained, in temporally fine-grained things going on, like transactions, and where you either want even more high-resolution snapshots, or even different ways of modeling it, like a link stream or integral graphs. And the three of us and sort of some of the wider Raphtory community have worked with temporal graphs for a little while, and we found that using some of the existing tools and ways of reasoning them, a few challenges along the way, and you can read the next couple of slides as describing some of these challenges and some of the motivation for Raphtory as a software. So the first challenge of working with temporal graph data in things like Python or any coding software that you want to use is that the code can be quite hacky and gets messy quickly. So as a little example, if you imagine that you have some social network data set of interactions, and you want to say, I want to get a weekly idea of the page rank scores of the centralities of the vertices of the network and how those are changing over time. So like a sliding window view of their interactions from the start to the end of the data set. Say you want to do a leaderboard or something. I bashed some code together using Python and NetSci-X for doing this, where first, let's say if we're using a Facebook data set of interactions, we're reading the data set using something like pandas, and we set up our time range that we're interested in and the sliding window side, and then run through this data set, filtering down to the week that we're interested in, make the graph of those interactions, and then run page rank or whatever algorithm we're interested in using NetSci-X. And this is okay, but I found that I ran into quite a few, say, the pandas errors to get this to the time filter to work for this. And also, it's writing code for this can be sometimes quite hard to modify to say, what if I wanted instead the monthly or annual all-time, or what if I wanted to do like a full range of different windows of interest or extra filtering. And I think another thing that we found is that the code can sometimes be inefficient and hard to scale to bigger data sets. So using the same same code for this, firstly, when we looking at this sliding window of building the network over time, we make several passes over the data to get those the interactions we're interested in, one for each time point, which is not great. And then also because we're constructing and then discarding many individual graph objects, again, each for the number of time points we're interested. It's okay for if it's maybe a small data set or a short time period, but if you're looking at large networks or long time periods, this can get inefficient or be harder to scale. And a slightly different but more underlying challenge we wanted to address that there's lots of different ways of how you might think of a temporal network. So people might see temporal networks as being like different snapshots of a network over time, where each of those might be a separate file or something. Sometimes we might consider a temporal network as how the aggregate graph evolves over time. So starting from time 0 up to now, how the graph is changing. Another way people think temporal graphs is have nodes and edges that have duration, particularly say in contact networks or things like this. And all these things are often, you have to write completely bespoke and original code for these different use cases. And this is, I think, not in any way criticism of the original network tools that are available, but because they're not designed with temporal networks in mind, it can be hard to adapt these, which is why we developed Raphtory as being specifically for temporal graphs. So first off, we'll have a look at the how we see a temporal graph in Raphtory. So the Raphtory graph model is think of as a stream of things that can be seen as graph updates or changes. So we have our timeline, and this is a stream of new information coming in about the graph. So things like vertices appearing, disappearing, and properties changing, and these happen at specific timestamps. So in this example, if we imagine it being a social network and some of the friendships or interactions going on, at first time 1, Ben joins the network with the username myritpuffin, and his friend Chris joins at time t2 with name soupnom. They become friends at time 3. He changes his username again. Then at time 5, they have a disagreement, and that link between them disappears, and then reappears after they've had a beer and talk about it slightly later on. And you possibly get the gist of the idea that we have this log of the changes that are happening to the graph, and all these properties, both the structural and the properties like usernames and things stored in the history. And this means, then hopefully might become clearer later, that we can understand a variety of different notions of temporal graphs. So that we can understand things like snapshots, where you have just static views of the graph over time. we can look at things like linked streams where the edges and instantaneous events like transaction networks, and interval graphs where edges and nodes have duration. And finally, the idea of time windows where you can say, I'm interested in the graph according to what happened between time 1 and time 2. So now that we have this graph model and way of seeing graphs in Raphtory, we want to ask, okay, how can we apply some of the algorithms that we know to these graphs? And they can be, thinking of graph algorithms, you can separate it in terms of the sort of scope of the graph, going from the very local, so things like asking a vertex what its degree is, properties like username, and not involving any of the wider neighborhood. You can go slightly more further out, expanding to ask about perhaps small subgraphs like triangles, things in the graph, expand into wider structures like community and components, as well as what you know about the whole graph. And I think that some of the algorithms we've got so far, and what we hope is for Raphtory to sort of span this spectrum of the algorithms that you can do in Now. And the way that we look at algorithms in Raphtory is by a paradigm called think like a vertex, or sometimes known as gather, apply, scatter. So traditionally, when a lot of the tools that are available for looking at networks think of it as the whole graph, so on one machine as a singular object. Whereas what we mean by thinking about a vertex is you look at the graph from the perspective of each vertex. So here we have node A doesn't know anything about the graph apart from its neighbors, node B, C, D, and E. And similar for node H here. And in this situation, each vertex has information about its own ID, its any properties that it's have, and its history within the scope. It has some information on its incoming and outgoing edges, and so the IDs of the nodes directly connected to it. And in addition to this, each vertex can send and receive a message along the incoming and outgoing edges. It can perform computations with some information that is received, and it can store state or values involved in an algorithm that's going on. And the reason it's called gather, apply, scatter is that first you gather information that's been messaged to you by your neighbors. You apply, so you might do some computation to that, and then based on what you've come up with this computation, you then send that on to your own neighbors. And what this means, thinking like a vertex, is that through this sort of repeated process of passing messages and doing computation steps, you go from knowing only about your immediate neighborhood to knowing more about the wider structure of the graph and graph quantities. Also, by separating down to individual vertices, you can, on the computation side, you can store vertices on different machines or cores, but meaning that you can scale up a bit better rather than having a single graph on one machine. And it turns out that many graph algorithms can be expressed in this way, and I'll go through some examples in the next few slides. So a local algorithm, a couple of examples of these, and what I mean by local is that no messaging step needs to occur. Is things like asking each node what its degree is, or obtaining a property. So the node here can immediately say, my in degree is 3 and my out degree is 1, without any messaging steps to occur. there are some algorithms that involve just one messaging step. So a good example is triangle count, where in this one, each node compiles a list of its neighbors and sends that off to all its neighbors as a message. And then A says, okay, I've got these lists of the various neighbors involved, and comparing these with my own neighbor list, I can work out that my triangle count is 3. And if you go further out, there are some iterative algorithms where it might take a sort of unknown number of messaging steps to compute. So there's things like page rank, which is iterative as each vertex updates its own score, connected components, and also there's some community detection mechanisms that work in this way. So for the community detection example, if we're the communities are represented by different colors in this instance, each vertex can propagate its own color label, and then having received the color labels from your neighbors, say which of the labels is the most common, and in this case the lilac was the most common out of those, so I'm going to update to lilac as well. And this is called the label propagation algorithm for community detection, and the idea is you go through this step of updating the labels over and over until the labels stop changing. And as we said, we're wanting to focus on the temporal algorithms in mind. There's some time information that can be incorporated into the algorithms as well. So say if we have a contact network where each of the edges represent some contacts that occurred, so some significant time spent together. And let's say this node on the left here finds out on Wednesday that it's positive for COVID as an example. Then this idea of the message passing in algorithms means that this message can be propagated to the central node of interest because they met just the night before, and then that can go even further to possible other nodes at risk. And this is a wider idea in some of the algorithms we use of propagating messages along edges that respect in time to trace things like dynamical processes happening on the network. And it just sprung to mind as well that some of these the processes mentioned in the previous talk of the game playing and the evolution of cooperation or defection could also work in this context as well. So once we have an algorithm and the data set of interest, what can we do with it? This is where we introduce the idea of graph perspectives and queries. So as an example, say if we have a data set of transactions that are going on where the nodes are people and the edges are some transaction of money from one to the other. We want to easily be able to say, I'll look at the graph within a desired sort of time selection procedure. So the first type of query that we can make on the graph is what we call a point query, which says, given a point in time, we want to look at the graph from time 0 up to this time of interest and all the interactions that happen between then. The second time is example is a range query where we say instead of just one of those, we want to space that out and say every hour or every week, how did the graph change according to the algorithm we're interested in. We can also construct a window view where, say, instead of the whole graph up to a time point, we want to just look at something within a particular window that slides along. We can also think to make things easier to look at batches of windows. Say, if you wanted an hourly or weekly or monthly result to be able to run those at the same time. And finally, we have the idea of a live query. So what's the what does the graph look at now? And it's especially relevant if you have if your data set is a source where new information is coming in all the time. And the reason we have dot framers is to make these things easier, rather than having to rewrite different filtering procedures to get these different views of the graph. You just change the query parameters, which Ben will cover a bit later. So putting it all together and in the context of a couple of examples, though I said that Raphtory was used in our study of the social network gap. And in this setting, we were interested in the time perspective from the point of view of of how the time window of analysis might change some of the results that we see. So we picked some sort of fairly basic network structure, things like the number of nodes, sizes of the largest connected component, and we're interested in how the graph looks over different timescales. So in this plot on the left, we were looking at the number of vertices, but according to either the aggregate graph, where it's just everything between time 0 up to time t, looking at the 6-month windows, 3-month windows, all the way down to weekly and daily ones. And if you were looking only at the aggregate graph, you would probably say that the graph is growing in quite steadily in the number of users, but it's only when you start shrinking those windows that you see that actually a lot of that growth is attributed to like bursts of users who might start using the platform and then might not even use it again. So you get like different stories according to the windows that you use. And then we also looked at things like size of the connected component, and we found a sort of interesting result, which was if you ramp the window size down to an hour and measure the proportion of vertices in the largest connected component, we found that this seems to form and shatter over the 24-hour period where when everyone's online in there's a largest connected component, and this shatters just into pairs of people interacting in the off hours. And as well as looking at sort of static graph algorithms, but just at different points in the graph over time, we also quite interested in temporal algorithms. So a recent example we looked at was those in the Ethereum network. Someone hacked the exchange there, and was it about a million Bitcoin?
Yeah, 50 million from up there.
Yeah, 50 million Bitcoins from the Korean exchange update. And now that they had that, they wanted to disperse that throughout the network so that they could clean the money. And we used the Raphtory to trace the paths that this money was taking through the graphs by looking at the time respecting paths going from that node and seeing when that tainted money hit exchanges where people were cashing out and things like this. And then we're also looking at temporal motifs and finding interesting patterns that can, there's an example, someone receiving 12 Bitcoins and then almost immediately splitting that transaction into 3 smaller ones later on, which can be an indication of someone trying to obscure something, or is a mixer going on. So at this point, I'm going to hand over to Ben, who's going to go into a bit more detail of how Raphtory works and how to interact with it.
Hello, guys. Yeah, so that's kind of the theoretical side of what's going on behind the scenes of Raphtory. So I thought you'd just give you a little delve into kind of how you would actually get the tool running if you wanted to, give it a crack on your own data sets. So just as a quick overview to this, there's kind of 2 sections to Raphtory as a platform. The first of which is your ingestion and modeling. So this is how you get your data into the platform and how you actually turn it from your kind of raw source into a actual graph. So we have what we call a spout, which is the first component of this. So this is the sort of the hole in Raphtory to the outside world, and that you can connect to databases, different streams. It could be HDFS, different distributed file stores, or files that you have locally on your computer. we have a tool or component called the graph builder. And what that will do is it will take a user-defined function, and for each tuple or sort of piece of information in your data source, you can turn that into a set of updates. So this is the creation and deletion and updating of vertices and edges that Naomi was talking about. And then we have a set of partitions or partition managers, and these are distributed across the machines that you have or just locally on your machine, which will store the full temporal graph. They'll synchronize with each other and make sure that all of the state and the history is available for you to query. Speaking of querying, we then have the other side, which is our sort of analysis. So we have an analysis manager which pops up whenever you spawn a Raphtory instance. And whenever you submit a query to it, it will spawn off a task which will coordinate with the partitions, run your algorithm on the specific perspective that you've asked for, and then return the results to you. So if we dive into getting your data into the platform, as I said, the first thing we do is we would decide on where the data set's coming from. So let's say we're connecting to a database. We may, in the friendship network, so in our social network example, may want to create a friendship builder. And in that, we're going to convert our updates into a set of friendships. So me and my mate Chris, looking very handsome there, are split between two partitions. It may be then that later on, we want to say, we've read in all of our database data, we then want to swap to a stream. Well, we can still use the same graph builder. We're just going to swap out to this stream spout. So this may, I don't know, connect to a Twitter API, something like this, where we're streaming in information in real time. Alternatively, in this instance, we may, we're done with the friendship network. We're going to try to interpret the data in a slightly different way. And we're then going to swap that to post comments. So we're going to, instead of extracting out the individual users, we're going to then build comment trees and see how different sort of posts generate responses. So that's, however, this then goes into the set of update streams, which will push into our partitions. The updates will flow in, these components will synchronize, and then you'll end up with the full graph history available. So the interesting thing here is that where we have this kind of full history log, we can actually blast in data sets in parallel from loads of different sources. And as long as they kind of all have the same time available in them, then this will all sort all the order out, and you'll always end up with the same graph. So if all your data is unordered in loads of random spots, throw it all in, and you can still query it. So yeah, so that's kind of the high level of what it looks like to get your data in, but I thought it'd be worth just having a quick look at what this looks like in practice. So if we have the character co-occurrence data set for Lord of the Rings that Naomi was talking about, and the idea here is that we have two characters and then a line in the book of which they first, when they bump into each other. So Gandalf and Elrond here on the first interaction on sentence 33 of the first book. For this, we create a Raphtory graph. This is written in Scala, which is it's kind of an in-between between Java and Python. If you're totally allergic to all languages other than Python, don't worry, we have a Python interface as well. And that's being improved upon right at the moment by some of my colleagues. So inside of this, we create our spout. So this is the most basic resource, basic spout we have available. There's a collection of them. You're happy to, free to use whichever ones are work for your data set. And this just takes a file called lordoftherings.csv. We create a graph builder. So there's Lord of the Rings graph builder here. And then we put these into a Raphtory graph. And then this is available to query. We'll go into the querying in a second. And then delving into the code for the graph builder. This is unfortunately a little bit blurry. But just going through the idea is basically we have one function called parseTuple. And this specifies for an individual line, how do we convert this into graph updates? In this instance, for those, I guess if you have a look back or for those online, we specify that we have a source node. So this is at position 0 in our string. We then assign that an ID. We have a destination node. And then we have a timestamp at which those occurred. So that then gets set into 3 graph updates. So adding the vertex 1, specifying that at the time that it happened at, and giving it some properties. So we've got a name, and we're saying it's a type character. Doing the same for the second. So in this case, our first node, Gandalf, is a character and his name Gandalf. Second for Elrond. And then we add an edge between these. So this is the bottom line here, where we say at time 33, source and destination co-occurred with each other. So this will allow you to kind of build out that full network and then to start running different algorithms on top of it. So with that being said, once you have the data in, what do the actual algorithms look like? So we have a 3-level API, which I think Naomi was alluding to earlier. The first of which is we have a nice wrapper for the vertexes and edges in the network. And this allows you to kind of interact with the history, to get the properties out, see who your neighbors are, and so on. And this is all wrapped up in a way such that once the algorithm is run, those will always return the correct result given the perspective. So if you say you're running it on Monday, you'll get a different answer to if you were running it on Thursday, depending on these parameters that you've set. Once you have, a little bit of lag here. There we go. Once you have the vertices access enabled, then we can actually start building up our algorithm, and that's done via steps. So this is where you will push out messages or calculate some state about yourself, store some individual state, and this happens once. We have steps but with iterations, in which case you run the same over and over again until you converge at some final state. And then once you've done these kind of graphy elements and converged, you can then select out the elements that you're interested in. And then that's how you define the algorithm. And then on top of the algorithm definition, you can now set some time parameters. So run this at single points, run these over ranges, run it at the most live point, add all your windows in, etc. And that algorithm will then churn through all of those different perspectives. So again, just to give you a little context of what this looks like in practice, for the degree algorithm, the zero-step algorithm that Naomi was talking about just previously, we have one function which we define, which is called tabularize. Go from a graph into a table. We're going to call our select, because we have no messages, we're just going to extract out some information. And what this says here is for each vertex, give us some information. And we want to get the in degree, we want to get the out degree, and we want to get the total degree. And now we're going to return a row for our table, which gives the name of the vertex and then these properties that we're interested in. Going into something slightly more complex, so looking at connected components in this instance. Just show of hands, everyone happy with connected components? Okay, interesting. Okay, so the idea of connected components is that if we have a set of vertices in a network, in this case, we're just having a look at they're reachable in some way. So if we've got, say, Naomi, myself, and Felix are all connected up, and then two guys at the back are connected as friends, we would form one component. We have no connection to them. They form a second component. So it's just a kind of a way of looking at the different communities that occur in your network that are reachable to each other. The way that we calculate here is in the gather, apply, scatter terminology. We have an apply stage. This consists initially of one step, where for each vertex, we set ourselves a label. So this is our component label, and this is just our vertex ID initially. And we then send a message to all of our neighbors saying, hey, I'm node X, let me know in the next step who you are. We then have an iterate, where for each vertex again, we say, okay, get me the minimum label that I've got from all of my neighbors. I'm then going to compare this new label to the one that I have inside of me. And if it's less than the one that I have, I'll then set that as my new label, and then I'll send that to my neighbors. So if Naomi was, say, node 2, and I was node 3, I get that message from her. I'd say, okay, well, 2 is less than 3. I'm now in component 2, and I'm going to then send that message off to Felix. If it was the other way around, I would say, oh, no, actually, I'm in a lower component, so I'm just going to vote to hold. So I'm happy I've converged, and then we'll continue doing this until everyone's converged. Once that convergence occurred, then we have a tabularize again, in which case our select is give me the name of the vertex and then the label which it was given finally. So this way, by sort of iterating over and over again, everyone converges to their final state, and then we can extract out that value. So that's kind of interesting if you want to go into the submitting of algorithms. However, there are a good chunk of algorithms that are already implemented, and in which case you don't have to touch that stuff at all. And in this instance, or obviously if you have written your own algorithm, you can go into this as well. We define our graph at the top, as we saw before, setting a spout and a graph builder. We can then submit a point query, where in this case we've submitted the degree algorithm we've just written, and we're running this in Lord of the Rings on line 30,000. Don't worry about the file output format, that's just sort of specifying where your data goes to. If we run a range query, we can do in this instance, say, set the connected components, and then we can see we've got some parameters down the bottom here. So we're starting at line 20,000, going to line 30,000, and incremented by 10,000s. And then we have a set of windows. So we're going to, at each one of those positions, we're going to look back 500 lines, 1,000 lines, 10,000 lines. So this is actually sort of 6 different perspectives looking at the graph, and then obviously you can expand these up to ridiculous amounts. I mean, in the example that Naomi gave for the Michigan Derayas data set, they had 400 years. I think this was something like 750,000 different perspectives over the whole period of time. So it gets to the point where it's sort of absurd numbers that are just formulated in this one query. And then finally, we can run a live query, where this would just run on the most recent point in time, incrementing forward, in this case, 10,000 lines. Unfortunately, Tolkien stopped writing for obvious reasons. But if he was to continue writing forever, this would ingest in more and more lines. The nice thing here, actually, so this is a new feature that we've just put in, is that we can also chain algorithms. So in this case, we're running a label propagation algorithm into an outlier detection one called CBOD. And in Raphtory, you can actually chain arbitrary numbers of algorithms to kind of build up more and more complex stuff. So finally then, if you are, as I said, allergic to Scala, you can actually just ignore all of this, or at least most of it, and get your data straight into Jupyter. So once a query is run, we can import our Raphtory client. You can then create a graph from a topic. So in this case, we've exported out an edge list. We can then get results for an algorithm that's run. So in this case, I run a PageRank, and that'll actually build a data frame. The client will also then have a NetSci-X graph inside of it that you can play around with, and then merge that with the other sort of general data analysis that you're doing. And then having a look at this, I plotted this out to have a look at the PageRank at different points in time for Frodo. So here you can see at time 30,000, we have a window of looking back 10,000 lines. He had a variety of different scores. So it's just like a little delve into what's available here. There's a full tutorial for all components of this if you want to have a dig and play with yourself. Yeah, sure. Oh, I cannot remember the name of this tool for the life of me. It is, yeah, it's an interactive dashboard that you can bring into Jupyter. I'll double check afterwards. Oh, no, so this is just general plotting inside of Jupyter. We're currently working on our own libraries to do this. So watch this space. It will be done soon. Cool, so that is a very whirlwind tour through how to use Raphtory. I just wanted to give a little idea of kind of what's on the horizon for us as a whole. Oh, there's a little UPM logo there that snuck in. So the first thing is that we're rebuilding the platform for larger and larger data sets. So I think the largest data set we've got in currently is just over 1 billion nodes, and we're hoping to make that bigger with some cool new tech. So anyone that's into systemsy stuff, please do come and chat to me. That's very much my area, and I'll talk for hours and hours and hours about it. We're building some new APIs, so the way that we're viewing algorithms at the moment is somewhat new. We're really interested in anyone working in this space to give us some ideas on if you think this is terrible, if you quite like the way we're doing things. We're always up for changing and taking on new plans, and obviously the integration with Jupyter, we're looking to improve that. And then there's also quite a few research and industry positions if you're interested. So if you're coming to the end of your PhD or a postdoc, there's research positions at UPM and the Turing, and there's industry positions available at Pometry if you're interested in moving away from academia. If you are as well interested in getting involved, hop onto the Slack, come and give Raphtory a try. If you Google it, it should be the top link, or it's just on GitHub. And then finally, thank you very, very much for staying this late and for listening to us go on. Please, if you have any questions, let me know.
So, open for questions. Now you can give the microphone to yourself, Ahmed.
Well, thank you for the very interesting presentation. Just have a couple of questions. Why should we use the Raphtory over GraphX, for instance?
I think the Spark GraphX.
Spark GraphX, yeah.
For sure. So I think if you're using Spark for, say, one individual point in time, then you may see some improvement over Raphtory currently. We're just about to release a brand new version, which I think will beat out GraphX just in general. But if you're running, let's say, a variety of different perspectives, or you're running temporal algorithms, so if you're actually interested in time-respecting paths, in accessing that sort of level of Raphtory, exploring the history, these things will just be horrible to write and will take a very, very long time to run. I mean, we were running on one data set, so again, this was on my laptop, not massively scaled out, but it was taking 5 minutes to run in Raphtory and will look to take about 3 months if I was to run it explicitly in GraphX. So there's a lot of performance reasons why you want to use Raphtory, but I think if you're genuinely interested in the temporal side of things, so actual temporal algorithms, the APIs we're providing make it much, much easier to write these algorithms.
Okay. Thank you. And do you have any plans or graph neural networks in integration with Raphtory?
Yes, so that's actually, one of the things that we're working on at Pometry is expanding into graph neural nets, doing some interesting machine learning on top of Raphtory. We're going to still provide the kind of open source algorithmic library, and a lot of these algorithms that we're working on will become open source. But yeah, we've just brought some people on board to work on explicitly that. So if you're interested, I'd definitely love to talk to you about it.
Okay, thank you.
Thank you. Hi. I had some curiosities about the library. The first one was about the RAM occupation. Are you using any sort of compression? So, let's say, a web graph. Is this a problem, or is?
Yeah, so this is actually a huge problem, and it's a great question. It's not the question I was expecting, but we was debating about how much of the system-y side of things to put in. But yeah, so at the moment everything is Java objects. However, one thing that we're hopefully going to be releasing in the next couple of weeks is we've moved everything out of the JVM heap, and we've put it into a standard called Apache Arrow, which is kind of byte arrays which allow you to kind of move between Java and C and kind of other low-level languages, so that we don't have all this garbage collection problem and other sort of heavy problems on top with the usual way that you'd allocate these objects. So yeah, so we're able to sort of 100x the amount of objects you're able to store in memory. We're also looking to store that down onto disk so that you can sort of have infinite size graphs on the same machines. But obviously, there's the degradation of it if you're loading back and forth. So yeah, that's exactly what we're working on at the moment.
Okay. And the second question I had was if you are supporting in any shape or form multi-layer networks.
Oh, what was that? Sorry.
Multi-layer networks.
So
temporal and multi-layer.
So we haven't looked at it at the moment. It's definitely something I'd really be interested in exploring, both from a systematic perspective and also an API perspective. One of my co-founders were looking at cross-chain communications and selling in the crypto world. So if you have kind of these dark exchanges which are accepting Bitcoin and spitting out Ethereum, or spitting out Monero or something like this, and then seeing if you could actually track across those or predict prices from one into the other. So yeah, there's definitely a lot of interest in our group to look at it. We've just not had the kind of push in that direction yet. But yeah, same with the GNN stuff. I'm really up to discuss these sort of things, how we'd implement it.
So the positions open would be about...
Very much so.
Thank you.
Hi, thanks for the interesting presentation. I was wondering which is the size and order of the biggest graph you tested?
Yeah, so the biggest graph that we've got in previously was the vast majority of the Ethereum network. So I think it was over 1 billion nodes. At the moment, we're looking to massively increase that. So that was on a very, very large cluster with sort of terabytes of RAM. And it's not the sort of thing that you want to be running for days on end. The most recent tests we had something like 240 million edges ingested into a 64 gig box, and that took about half an hour. So we're sort of trying to ramp that up as much as possible. And I mean, there's kind of 3 or 4 people that are dedicated to kind of making Raphtory go fast and go big. So those numbers are kind of spiraling out of up and up at the moment.
Okay, so I'll follow your work.
Thank you very much.
Thanks.
I think let's thank the 2 speakers again.
Thank you very much, guys.
Okay. Just to finish and wrap up, I think you all look a bit tired, not too much. It was because you did not analyze by hand 1 billion nodes of the network. So I hope to see you all again tomorrow. I hope you enjoyed the first day of the conference and have a good night of sleep. Enjoy Porto.
you.